theoretical aspects of computer science, looking at why are some problems hard and why are some problems easy for a computer to solve. And I must say, Prahladh has a very interesting connection to the world of art. He is a trained Kuchipudi dancer as well. So, over to you.
Thank you, Arnab, for the kind invitation. Thanks all of you for joining. Welcome and thanks for coming to this occasion, and thanks to Junoon for inviting me to give this talk. I'm delighted to speak about hardness and easiness through the computational looking glass. Arnab already mentioned that before going, this is not working. Let me just say a few quick words about myself primarily my home institute. I come, for those of you who do not know, I work at the Tata Institute of Fundamental Research. This is an institute dedicated to the study of the basic sciences, and I work in the computer science division of this branch. If you've not been here, if you've not been to the campus, you should certainly visit us out here. Anyway, that said, let's get started. This talk will comprise, it's going to be on the talk of, I'm going to be talking about easiness and hardness, but everything from a computational point of view. The talk will primarily have three parts to it. In the first part, we'll be talking about a variety of problems. I'll introduce it to what problems. The second part, we'll go back to these problems, find out which of these are easy, which of these are hard, and then try to answer how to deal with this. Now, when stated this way, this is no different from sort of our everyday chores. Every day we start up, we have a bunch of problems. Actually, now that I look at the slides, the word problem, I should not be using it. Problem has a negative connotation in English. Whenever I say problem, think of it as a task. So we have a bunch of tasks, we have a variety of tasks, and we would like to find out which of them are easy, hard, and then correspondingly solve them. So what's the difference between a day-to-day? The only difference is I'm going to look at this from the computational lens. I'm going to look at all of this. So I'm going to look at primarily, not all, but primarily problems which have a computational flavor to them. And given this computational flavor, we're going to ask which of these problems are easy or hard in a computational sense. This discussion will lead us to various topics in computer science, which in the computer science jargon are called P, NP, and eventually the P versus NP question, which is a big question, open question in computer science. And finally, this will be, the second part will be the major bulk chunk of my talk. I'll spend a considerable part of the talk on this, trying to understand what does it mean to be easy, what does it mean to be hard. And finally, depending on how much time we have, we'll come to question of easy problems. Of course, they're easy, we don't have to deal with them. How to deal with hardness? How do we given that we feel that certain problems are hard, how do we actually work with these problems? And in particular, can we actually harness hardness in a positive sense? These will be topics. By the way, I would like this talk to be as interactive as possible. So feel free to stop and interrupt me. So it's not necessary that I have to cover all these topics. It's better for us. It's better for me if you feel so questions that will make it more entertaining in this one for all of us. Let me start with giving you a variety of tasks. Some of them will not be computational, some of them will be, most of them will be computational tasks. So let's start with what do I mean by a task or something. Let's start with something very basic. Say if we suppose a fitness goal, some of which have, or some of which you would like to have. So say I would like to come up with a fitness goal, I would like to run 7 kilometers 3 to 4 times a week. This is a goal I have. Some others might have a goal that I want to swim 30 or 40 laps thrice a week, or I want to be able to run a kilometer in less than 5 minutes or so. Each of us might have our own respective fitness goals. That's sort of what the final output we want of our goal, of our task. But of course, we need to be realistic. Where do we start with? It's based on our current fitness levels, our current sense of discipline. How much discipline do we have to attain this particular final goal? And of course, age also plays a role in all of this. So this is the input. This is what we have to work with, and that's sort of the goal which we would like to achieve. And we would like to achieve, this is the task at hand. I want to take this input, translate it to this, and see how we eventually managed to achieve this. I did mention that the tasks which we have are easy, some of them are easy, some of them hard, or some of them possibly impossible to solve. So this is one such task. So all the tasks which I have will have this basic feature. They will be an input which we are going to be working with. There will be a target output, and we'll be interested in how to get from the input to the output. The most interesting part of it is this part, is the blue arrow I'm going to be talking. I'm going to give a variety of such tasks. This is not a computational task. I'm going to give a variety of such tasks. And what we'll be interested is actually how do we implement this? Given a particular input that we have, how do we translate it to the output which we have, and how easy is it to do this translation? That's going to be the focus of the talk. So this is one such task we can have. A more other mundane, so this one is possibly say a task of a postman or a courier person every morning. So each time, say a Flipkart courier person goes to reports at work every morning, what does he get? He gets a bunch of parcels, a bunch of packages and letters, and a list of locations which he has to drop them off. This is sort of, he gets a bunch of locations, parcel 1 here, parcel 2 there, parcel 4, parcel 5, parcel 6. This is his input. This is what he gets when he returns in at work. And based on this, he wants to come up with a route connecting all of this so that he finishes his work at the fastest point of time. That's what he wants to do. He wants to check, can I deliver all these parcels, say by lunchtime, say in another 4 hours, 3 hours. So this is the input he has. And what he wants to ask is, can he somehow, what's the best route to connect them? So his input is the set of locations and the interlocations times. So between every 2 locations, I tell you how much time to get from location A to location B, say Bauda Gillard Museum to TIFR to World Trade Center, and all of these. Once he gets to have all these interpoint locations, and based on this, he would like to come up with a route that's as fast as possible. Say he wants to finish it he wants to get done at the earliest. This is one such task. This is in the computer science jargon, we typically call it the traveling salesperson problem. But for the purpose of the talk, I thought it's better to call it the Flipkart delivery problem. This is what the delivery person at Flipkart sort of faces every single day. So this is one task which we will talk. We will come to the computational aspects of this talk. Another task, we might not call this a task, but is the solving of the Sudoku puzzle. Many of us know what a Sudoku puzzle is. We are given this sort of 9 by 9 board, and we need to fill it with numbers from 1 to 9, so that every row and every column has exactly one of the digits from 1 to 9, and every square also, each one of these 9 squares has exactly one of the digits. This is a Sudoku puzzle. We want to take this and translate it to possibly something like this. We don't like to call this a task, but actually the reason it's a difficult task is what is challenging. The reason we like to do this is because we think it's a difficult task, and the fact that it's a difficult task impresses us that we have done this task. So this is another such. Sudoku is a puzzle, but this is also, I'm going to call it a task. From this particular input, I want to translate it to this output, and I want to know what is the complexity, how hard is it to do this translation. If you're going to talk about Sudoku, certainly there are harder games. I want you to talk about chess. Chess is a 2-player game, but let me phrase it in sort of a 1-player setting. So suppose I'm given a chessboard with a particular position on the chessboard. We can ask, if this is the position, and if white is going to play next, does white have a winning strategy or not? Given this position, does white have a winning strategy or black have a winning strategy? This is a question we can ask. So given this as my input, output. So the thing to notice in all these examples I'm giving are basically all the tasks that I'm talking about are tasks in which there's a specified input, specified output, and we are interested in how to get to the output from the input. And notice that not all of them, this is an immediate, this one. There's a fair amount of work to do, and I want to understand how much work is to be done to this one. So there's an input, there's an output, but the most interesting part of the talk is going to be what goes into this blue arrow over here. So this, I'm going to give a fair several. So feel free to stop me, and if you don't, this is one such task which we have. Yet another task is, say, this is what we sometimes call the coloring problem. So suppose you're given the map of some place. In this particular place, you're given the state map of Maharashtra with all the districts marked out. So this map is not so well to read from far, because particularly I've given the same color white to all of it. So one question can ask, can I color this map with such that no 2 adjacent districts have the same color, so that I can clearly see what this one. So basically I want to ask, given such a map, I would like to color it this way. Of course, you can do it if you're going to give a different color for each this one, but I would like to do it with as few colors as possible. My color palette is very limited. I only know red, green, blue, yellow, violet, indigo, and all are similar colors for me. I don't know, so I would like to do it with as few colors as possible. And so the question we would like to ask is, given such a map with this ones, we know which two things are adjacent. Based on it, I want to give a coloring of this map so that no two districts have the same color. So we want to ask the complexity of how hard this problem is. And for those of you who know, actually, because this graph can be drawn on a plane, this actually it's known that you can do this with 4 colors. The interesting thing will be whether you can do it with 3 colors or not. That's just an aside, but this is a question. So far, we have been talking of tasks which we face, but we can also task of which as a community we face. There are multiple types of tasks. For instance, just a couple of days ago, the Supreme Court had a task before it. It had the Nautej Johar versus Union judgment. They had to pass a judgment on it. In that case, their input in that case was the Constitution of India, Section 377, the various petitions, the government reports, past judgments. They had all of these together. They had to process this and finally come up with the judgment. This is also a task. It might not be a computational task, but this is the input they had to deal with, and they had to come up with this judgment, taking whether this section is consistent with the basic principles laid out in the Constitution. Each of these are tasks, and what we would like to ask is how hard or how easy are these tasks being performed by each of these. One. Another task which we are all very familiar now with is the Aadhaar database search. All our identities, or at least most of our identities, are already there in the Aadhaar database out there. It contains our identity, our biometric details, our fingerprint scan, all of them out here. So each time an identification of one of us we have to, when an identification check is we go somewhere to one of these things, we give in our fingerprint or our iris, our eye scan. There's a check that takes place, and it says, yes, we are we, I am I. It makes an identity check. So there is this task sort of going on. There's an Aadhaar database search. Each time you go, when you're checking with a SIM card or something, there's a check going on here. Of course, the Aadhaar issue is a slightly more involved issue. We would like to do this with a further privacy guarantee of the individuals passing this one. But this is also a task going on out here. There's a task in which this is the input. I have the input, which is a database of all the individuals and their biometric details, somebody's fingerprint scan, and I want to check who is this person. That's the task involved over here. You'll have to sort of scour through this database to find out if this individual matches over here. So this is one example of a task. So far, we've been talking of tasks more from the real world, but let me now shift to sort of tasks which come from mathematics and stuff, which even simpler tasks, actually tasks which we learned in grade school and stuff. Let's just start with the simple stuff. So the previous tasks, I do not know how easy or hard they are, but these are something which was taught to us in first grade and second grade. We certainly know. So given two numbers, we can ask, what's the sum of these two numbers? Certainly we know how to do this. We were taught this in first or second grade. This can also be framed in the language of the task which I'm talking. You're given these two numbers as input, and you want to translate it to this number. This is the task at hand. What you want to do is get the sum of these two numbers, and I want to ask how hard or how easy this task is. Certainly, among all the tasks we know all the tasks I listed out, we know that this task is an easy task. This was already taught to us at first grade. I'm going to spend a considerable amount of time later in the talk to understand why actually we call this task easy from the computation point of view. This is addition. If I'm going to talk about addition, certainly one can talk about the next thing which we learned in grade school, which is multiplication. So you're given two numbers, and you can ask what's the product of these two numbers. And the corresponding task here is the same thing. You're given these two numbers, you want to find this one. I want to ask how hard is this operation which takes these two numbers, computes the product here. This is multiplication. And these two were taught to us in school. Notice that once you have such a thing for multiplication, you can ask, what does multiplication do? It takes two reasonably small size numbers and produces a slightly larger number out of them. It's a product of this. You can ask the reverse process also. Given this number, can you break down into its components parts? This is the reverse of multiplication. You can ask, if given 1541, let's even take a simpler example. Say 2 into 3 is 6. Given 6, can I get 2 into 3? This is what is the problem called factorization. You want the reverse of multiplication. You can ask how easy this task is. This is a very natural question to ask. Strangely enough, this was never taught to us in school. how to do factorization, and there are reasons for this. And we'll see that why factorization was not taught. We never give taught, we were taught algorithms to do addition, algorithms to do multiplication, but not an algorithm to do factorization. So what's factorization again? Factorization is given a number, I want to break it up into two parts such that the product of these two numbers is this number. Of course, when I say this, you can sort of cheat and say I can always give this factorization. I can always give 1 into that number itself. This is sort of a cheat, and this we'll call it the trivial factorization. So the factorization problem will actually be given a positive integer n, obtain a non-trivial factorization if 1 exists. I don't want such a factorization. If such a factorization exists, give me 1. Notice I've added the word if 1 exists, and when you should ask, why am I asking if 1 exists? Don't all numbers have non-trivial factorization? That's not true, because there are certain numbers, the prime numbers, which do have only trivial factorizations. For example, 2, 3, 5, 7, the only factorizations are factorizations of this type. They cannot be broken down into this part. Like 23, for example, is just 1 into 23, whereas on the other hand, there are other numbers like 24, which are multiple ways of breaking them down. 24 has, you can break it into 2 into 12, 3 into 8, 4 into 6. I think I've got all of them right. Yeah, so these are multiple ways. So if what I want for the factorization problem is asking, given a number n, can you break it up into two components, which is a non-trivial factorization? So this seems like a very natural problem, but unlike the previous two things, we were never taught this. And why were we not taught this? I'll come to this later on in this one. The previous two, addition and multiplication, are easy problems. This we were not taught, and we'll come to that later. Now, given this question, we can ask, factorization is asking of breaking a number into its two parts. You can just ask even a simpler question, can you ask if a number is prime or not? Basically, given a positive number, check if it's prime or not. Certainly, if I can do factorization, I can do this. But this is, in some sense, a simpler problem. For example, if I give you 23, I want to say yes. If I give 24, I just want to say no. In the previous case, I wanted to actually break it up into its components. So this is, certainly if I can do factorization, I can do checking if a number is prime. But neither of this was taught to us in grade school. We were not told, we were told what prime numbers is. We were told what factorization is in school, but we were not taught algorithms to do this in school. And we'll try to understand why for some problems we were given algorithms, for some problems we were not. So this is sort of the range. We started off with some everyday tasks. We went on to tasks of community is this one, and then we went on to tasks from arithmetic and number theory, and we just did a bunch of tasks. All these tasks had the common feature that there's a particular input, and there's a particular type of output, and they're interested in how to go from the input to the output. So we asked is, how easy is this transformation to go from the input to the output? Is there an algorithm? Is there a method to do this transformation? That's what we're going to be asking. That's going to be our basic question. Is there all our problems, all our tasks have been of this form. There's an input, the specific set of inputs, specific set of outputs, and we want a procedure. What we want is, we are asking, is there a systematic procedure, a step-by-step procedure to translate the input to the output? In the case of addition and multiplication, we were taught how to do this. For the other problems also, we would like to do this. Note this, I want a step-by-step procedure to do this, a systematic procedure. This, you can't expect a procedure out of the blue. For example, the fitness goal was not a computational task, but you can't say one morning decide, I want to be able to run a kilometer in less than 5 minutes, and jiffy, you have it then. You will have, it's a step-by-step process. It takes a while. Given the current fitness step, it's going to take. So we're going to ask, is there a step-by-step? In that case, you're asking for a step-by-step fitness regimen, which will take you from your current physical state to this particular thing. In general, we're going to ask for each of the problems, is there a step-by-step procedure? And that's what I'm going to call an algorithm over here, this step-by-step procedure. By the way, this seems sort of very natural to us, this one, but I'm being very vague here. What does it mean step-by-step? How small is each step? How basic is each step? And this is a problem that actually humans have been sort of trying to understand since time immemorial. The notion of what an algorithm is took millennia to crystallize. It's not, humankind has been trying to understand this for quite some time. In fact, started well about 2,500 years ago when the Greek and the Indian mathematicians were working in their respective fields of number theory, geometry, linguistics. It's like, for instance, Euclid gives an algorithm for computing the greatest common divisor. Pingala gives an algorithm for computing repeated squaring. Panini gives sort of a generative grammar for Sanskrit. And all of them, they never said that they were doing a step-by-step procedure, but what they were in principle doing is giving an algorithm, is giving this one for the respective problems or tasks they were studying. And this has been going on long, long ago. Primarily, it was initiated in the world of mathematics, but then it spread to other fields also. Now, 1,000 years later, Al-Khwarizmi, from a Persian mathematician who was primarily in Baghdad, wrote a treatise on the mathematics, primarily mathematics from the arithmetic that the Indians were doing at that point of time. And in fact, the word algorithm comes from his name. Al-Khwarizmi from Baghdad, his name algorithm is actually derived from his name. These were all trying to understand what does it mean but to do the step-by-step procedure. But till about 80 years ago, we didn't have a formal definition of algorithm till Alan Turing gave it in 1936, gave a formal definition. And so today we sort of do understand. For the purpose of this talk, I'm not going to go into what I formally mean by an algorithm. That's going to be beyond the scope of this talk, but I'll try to illustrate it with some of the examples for the tasks which we talked about. For addition, multiplication, what does it mean to do this? For factorization, for primality, what do these things mean? So this is what we're going to be trying to understand. We're going to understand for each of the tasks mentioned and for even other tasks, what does it mean? How hard or how easy are these tasks? So that more or less comes to the end of the first part of my talk. We'll now go into trying to understand what does it mean to call some of them easy, some of them hard. Two of them we of course definitively know to be easy, that's addition and multiplication, but we'll go into it again and try to understand why we call it easy. Of course, now here you should stop me and ask, just like beauty is in the eyes of the beholder, easy or hard should be in the ability of the doer. What might be easy for you might be very hard for me. So easy or hard is potentially, at least the way used in the English language, it's a very subjective definition. It's not this one, but what I want to impress in this talk is actually we'll be talking about I'm going to give a computational definition of easy and hard, which is not going to be a subjective definition. There's going to be a notion of what easy means and hard means, and that's what we're going to be working with. So easy or hard is whether it's easy or hard for this notion of a computing. Is it easy to compute this task? Is it hard to compute this task? So let's begin with the easiest of the tasks which we had, so addition. So we suppose this was the example we worked with. We know that 12,345 plus 6,789 is 19,134. Actually, let's take an even easier example. Let's take single-digit addition. Let's say we're going to do 5 plus 3. We know this is 8. What were we taught in grade school? Says 5 plus 3 is 8. So how does one, is this big enough or should I write? Actually, I could just use the board. So this one. So 5 plus 3 is 8. What does this mean? It means to 5, we increment 5 3 times, we are going to get 8. 5, you add 1, you get 6. You add 1 once more, you get 7. You add once more, you get 8. So 5, you take 3 steps from 5, you get 8. And so that's what it means to do. So let's try to do the same thing for 12,345. You add 1, it becomes 12,346. You add another 1, it becomes 12,347. Now notice that this is not the way to do addition. If I going to keep doing this, this is all I'll be doing till the end of the talk. I'll be adding 1 6,789 times, and I will never, it's going to take me quite a while to do this. So this is an algorithm for addition, adding it step by step, but that's not the way we were taught addition. We were told that this is what addition means, that is increment 5 3 times and you get 8. Increment 12,345, 6,789, and you'll get this. So this is an algorithm. But of course, if you do this algorithm, that's the algorithm we're going to be doing for addition, none of us would call addition an easy algorithm. So you have an 8-digit number and another 8-digit number, you add them, you're going to take eternity to keep adding. You have to take so many steps. But we do addition significantly faster than it. And why? How does that happen? So that's here. That is basically, you write down the two numbers, one below the other, so that the digits match, and you scan it sort of start from the rightmost column, you add these two digits, 5, 4, 14, you take a carry of 1, add this, 13, carry of 1 again. Am I doing it correctly? Yeah. 1, 9, 1, and you keep doing this till you come to a column where there is nothing over there. That's what it is. So scan the column from right to left. If empty, stop. Add the digits, right answer, and retain the carry. Move one column to the left, right carry, go back to 1. Keep doing this process repeatedly. This is what we were taught, and this is quite a remarkable. Doesn't seem, the face of it, this doesn't seem like what addition would do, but it exactly gives us the answer. This is an animated version for it. It's easier to do it that way, so bear with me for a few seconds. So this thing might seem more painful than the other algorithm, but certainly should appreciate that this is much faster than adding 6,789, taking 6,789 increments to the other number. So what this example I just want to impress on you is there are these two different algorithms for addition, but certainly we see one of them is better than the other. One algorithm, in fact, can we sort of see what's the difference between these two algorithms? In the first algorithm which we had mentioned, how long is the algorithm going to run? The algorithm is going to run at least for 6,789 steps. Those are the number. You have to do so many increments. Whereas this algorithm only depended on the number of digits over here. It didn't require what's the value of this number. It just ran in the time required to write this number down. This number took only 4 digits to write down, so it sort of takes 4 or 5 digits. It takes something like 4 to 5 steps to do this whole operation. Whereas the other algorithm, which is also a correct algorithm for addition, it's a perfectly correct algorithm. It gives the right answer, but that's going to take 6,789 steps to do addition. So clearly between these two, you can see which is the easier algorithm for addition. I'm making a big fuss about this, but what I want to say is actually it's not just me who made a big fuss about this. This is called the method of the Indians. For a long while, this is one of the biggest exports from India. It was sort of chronicled in Brahmagupta's Brahmasputa Siddhanta, where when the Indian numbering system was being discovered, that was said this is the way to do arithmetic. You add numbers this way. This was then transferred on when Al-Khwarizmi in his book, where the title of the book says the Book of Addition and Subtraction according to the Indians. So this was transferred and then further transferred to the West, the Latin translation of Khwarizmi's book, which is Algorithm de Numero Indian, the Indian art of reckoning numbers. So in fact, even as recent as the 12th century, in Leonardo Fibonacci of Pizza says the method of the Indians surpasses any known method to compute. It's a marvelous method. They do their computation using 9 figures and the symbol 0. So these two algorithms, right now we might take this algorithm for granted, this way of addition. It's taught to us in first grade, it's the addition, but this, in the understanding of mathematics in this one, it was a remarkable algorithm. It helped suddenly speed up doing arithmetic and this one. So I just wanted, so these are already, tells you why having this algorithm made addition easy, this one. Of course, we already see it. The thing is, this algorithm scales extremely well with input sizes. The previous algorithm which we saw, the 5 plus 3, it works well for small. If you had 5 and 3, I know how to do it. If I had larger numbers, it just blows out. The rate at which the other number blows with the input size, it just exponentially blows up. Whereas this one, if there's 1 digit, it possibly takes some 8 steps. If there are 5 digits in the numbers, as in this case, it possibly takes 40 steps. There are 10 digits, it takes 80 steps. It scales very nicely. If there are n digits, if this was an n digit number, it possibly just takes 8n digits, unlike the other one which depends on the size of the number. So addition, this method of addition scales very nicely. In fact, it scales linearly with the input size, and that's what makes it this one. So when we talk about algorithms, what we'd ask is we'd first like to come up with a procedure and then ask how does the procedure scale with input size? As the inputs to the problem become bigger and bigger, how does my algorithm work? For instance, suppose somebody says they have an algorithm to solve Sudoku puzzles. Yes, possibly you can take this. The usual Sudoku puzzle is a 9 by 9 square like this. You can solve it, and most of us can actually at best 20 minutes or half an hour of it, do an exhaustive search, and we can figure out what's the solution for it. But suppose you said you had an algorithm, a good algorithm for it, then a test bed for it would be then tried not just on a 9 by 9 thing, but on a 16 by 16. This you might be able to do it in half an hour. This, possibly it might take you a day for it, and then you go further ahead and then go on to, if you try the test bed on a 25 by 25, this one, I'm sure if you'd, none of us have an algorithm that's going to be doing this. And we're going to spend a couple of days or possibly a couple of weeks if you're just going to do an exhaustive search and try to do. So currently, we do not know of any sort of systematic procedure by which we solve Sudoku. We know how to do this, which we challenge ourselves with, but we don't have things which scale with input. This possibly you can spend a little time, but already at 25 by 25, it's well beyond our current means. We don't know how to solve this. And this is the reason why Sudoku, if Sudoku had an algorithm, we won't be solving it. There's no fun. Once something becomes easy, it's not fun. That's the reason why we are doing it is because it's a hard problem and we sort of feel challenged doing it. And we are working with the simplest thing. If you want a little more challenge, you should look for Sudokus of this size and slightly larger sizes and see how you could do. So this is an important thing which we want with our algorithms. We want to understand an algorithm. We will test, the test bed for our algorithm will be how it scales with input size. The addition algorithm was an excellent algorithm because it scaled extremely well with input size. So once you don't have to, it's not complicated. I could teach my nephew who's in first grade, addition works for 4 digits, and he'll automatically know how to do addition for 10 digits. It's not a much significantly more complicated. It's in fact exactly the same algorithm which I wrote there works for 5 digits, 10 digits, 100 digits, and so on. But the tricks that we usually know for this Sudoku puzzle is not going to help us for this Sudoku puzzle. These are very different. We don't have currently we don't have an algorithm, and I'll come to this question as why we don't have an algorithm for Sudoku. No, so what, in other words, I'm interested in how the algorithm sort of translates. For example, if you're interested in coming up with an algorithm that solves the Rubik cube puzzle, if you're not able to do the standard Rubik cube, what to do initially to find out if you have a method to solve the 2 by 2, hopefully you have, and then sort of slowly generalize it to larger and larger cubes and see if you can solve this one. So what we'd like to do when we say we have an algorithm, we want an algorithm that scales well with input size. And sort of re-emphasizing this over and over again just to show the difference between the two different algorithms for addition that we had. The first one scaled very, very badly with the input size, whereas the second one has scaled extremely nicely with the input size. And that's the reason why we're going to call long addition the addition easy because of the previous algorithm which we had there. And by the way, you should ask me, easy, hard. Easy, hard is typically because of some resource. We say something is easy because the amount of resource I'm expending on it is not too much. And obviously, already by what I said, the resource that I'm talking about is computational time. How much time is being spent? So this easy or hard is going to be, at least for the purpose of this talk, I'm going to stick to time as the resource. How much time does it take to solve this problem? Of course, depending on your context, you can talk about easiness and hardness with respect to other resources. You can ask how much energy you expend in solving a problem, how many rupees you need to spend to solve this problem. That's a different type of resource. How much space you need, what's the number of people required to solve this. These are all various different types of resources. And all of these are actually, you can study this for every problem. You can sort of every task, depending on the context, you can study its complexity or easiness or hardness with respect to the corresponding resource. At least for the purpose of this talk, I'll stick to computational time as the resource. I'm going to ask how easy or hard a problem is with respect to time being the resource. Of course, even time being a resource is sort of, you can ask, is that really a realistic resource? Because computers have become faster and faster with time. What used to be, certainly the computers I used in high school are far, far slower than even my cell phone over there. So does time being a resource? Isn't this also a subjective notion of easy or hard? Doesn't easy, hard change with this one? In fact, there's this thing called the Moore's law which says processor speed is sort of doubling every 18 months. This used to happen in the past, but it's sort of plateaued out recent years. But here is where we have, we're not going to talk about computers on a particular computer. We're not going to talk about computational time on a particular technology or something. We're going to talk this is where the notion of the abstract notion of algorithm came due to Alan Turing in 1936, Turing and other fellow mathematicians. We're going to talk about an abstract notion of computer, and this is sort of going to give a technology-independent notion. For example, to analyze the previous addition algorithm, I really didn't need which computer I'm talking about. I could talk about its complexity independent of which. It doesn't matter whether I'm doing it on my Mac or doing it on a phone or this one, and that's the sort of complexity. I won't be focused on any particular this one, and we'll be asking in that particular model, how does it scale with respect to one? This is an abstract notion. Hopefully it will get, I'm not going to go into the details of it. Feel free to ask me after that, either in the question session or after the talk on how to conceptualize this notion of this one. So that was all of this discussion was for the easiest tasks among our list of this ones. Let's try to spend a little time on each of the other tasks. So the other task which we also know was easy was multiplication, and this figure should sort of remind you, this is how we were taught multiplication in grade school. So you have two 8-digit numbers. You sort of multiply them out this way. In fact, notice this has about 64 digits out here. So this whole process to multiply two 8-digit numbers, I took a 64 other digits to write it down. So this was the grade school multiplication that taught to us, and it's because we know this algorithm for multiplication, we say multiplication is an easy algorithm because we have this algorithm in the hand. In fact, the fact that unlike, if you notice that this algorithm is not as fast as the addition algorithm. The addition algorithm scaled linearly. If you had n digits, the amount of time taken was something like proportional to n, whereas this was about n digits, it's actually n square. In that sense, multiplication is a little harder than addition. You can, yes.
If the number of digits are different for multiplication, then which n we should consider?
So then just make it the product of, so if this is an m-digit number, this is an n-digit number, it will be an mn, yes. So the multiplication which we have been taught is an mn time algorithm over there. For a long while, this was the best algorithm for this one. You can ask, this shows that multiplication is easy, but multiplication is not as easy as addition, and we sort of do feel it. Even when school, multiplication is always a little harder than addition. And this is one of the reasons is multiplication took sort of a quadratic number of steps, whereas addition took a linear. This is a way of quantifying why we felt multiplication was harder. The multiplication took a little more time than the addition algorithm which we had. And that sort of tells you why this one. Of course, you can say, is this a reason? There might be an algorithm for multiplication which runs faster than this. This is possible. This is what was taught to us. Just like addition, I gave you two algorithms. For multiplication, there could be a more efficient algorithm than this, which makes multiplication smaller than n square. In fact, today we know that multiplication this is not the grade school multiplication. Today we do know, due to algorithms, due to Schonhage and Strassen from 70s, that there's an algorithm which does significantly better than this. It's n log n complexity, which is better than n square, but not yet as good as linear. It's somewhere intermediate between n square and n. So we do know how to do multiplication faster, and this is how multiplication is done in practice these days, not this one. This is a significantly faster algorithm. So, but yet multiplication is sort of, this is the current known best algorithm for multiplication. And what we can ask is in fact it's open, can we make it even better than this? Can multiplication actually become as fast as addition? And this is an open question. We don't know this. Okay, so far we talked about two problems. We understood that they are easy. But even trying to understand this notion of why they are easy took us a fair amount of time. We do have an intuitive reason why they are easy, because we do have algorithms for it. But the algorithm is easy because these algorithms scale well with the input size. One was a linear time algorithm, one was a quadratic time algorithm. In some other cases, we might have a cubic time algorithm, or this one. Each of these, the algorithm which we have very nicely scales with the input. Whereas the other algorithms for the other problems, like, for example, the other algorithm for addition which we had doesn't scale. In fact, it scales exponentially for it. So based on this, we're going to sort of define what I'm going to call the class P. The class P is going to be the class of easy problems for us. It's going to have all problems that have easy algorithms. Are called, formally what I mean is a class of problems which have polynomial time algorithms, for which there exists an algorithm that scales well with the input size. It scales in a polynomially with respect to the input size. You can make this more formal, but that's good enough for us. So in this thing, so addition and multiplication were two examples of problems that fell into this class. So if this represents the class of problem which I call easy, which is called P. P stands for polynomial time. What we have seen is addition is in this class, multiplication is in this. What about the other problems which we have talked about? Some of the other problems which we talked about are, say, like map coloring, the Flipkart delivery problem, chess, Sudoku, factorization. These are all problems. What I would like to understand, are these problems also in P? Until date, we do not have easy algorithms to solve these questions, to solve these problems. These problems are still, we don't know how to put these problems, and that's going to be the focus of the rest of my talk. For the rest of this, these are what problems seem to bother us. We would like to solve these problems. We'd like to have a nice algorithm for chess. We'd like to have a nice algorithm for Sudoku. Of course, that will spoil the fun in Sudoku. It's the same thing with chess. If there's chess, the reason why it's an interesting game is because there is no this one. It's a challenging game there. But we would like to ask, why are these hard problems? We would like to see, is there a method in their hardness over here? So let's take some of these problems and try to understand, is there something more? Right now, we don't have algorithms for them, but can we say a little more about them? Why we don't have algorithms? Do these hard problems relate to each other in some sense or the other? So let's take some of 4 of these hard problems. So for example, map coloring, Sudoku, Flipkart delivery, factorization, and not included chess in this, and I'll come to it why I have not included chess. These 4 problems are going to have some feature among them. Recall each of these problems. Map coloring, you're given sort of a map and you want to color it so that no 2 adjacent districts have the same color. Sudoku, you had this puzzle, you want to fill it. Flipkart, you given a set of locations and you want to find out a route such that you're asking if I can find out a route map so that you can be done in a particular amount of time or not. And factorization, you're given a large number, you want to sort of break it down into its component parts. These are the sort of problems we asked. And the 4th column here seems like strange numbers I'm putting out here, all exponential numbers out here. What these numbers represents are the current best algorithms for these problems. We don't have any but unlike addition and multiplication where we had a linear algorithm or a quadratic algorithm, these are all exponential. These are the running times for the best known algorithms for these problems. These algorithms take, for instance, when you already have a map with say 50 districts, this algorithm runs in 2 power 50 times, the current best algorithm. That's far, far more than the age of the universe. So you can't be, none of these algorithms are practical algorithms. You can't be running these algorithms to do this on any, unless it's a very, very small size problems, you can't really use these algorithms. So what I would like to ask, are these algorithms what? So these are all hard, we don't have algorithms for this. We'd like to, is there a method to this hardness? Is there something else about this? One feature we will notice among these problems is, even though these problems are hard, suppose somebody actually colors this map. Once they color it, I can check that this coloring is a correct coloring or not. So I don't know how to color it, but somebody colors it, I can check if this is a valid coloring or not. Same thing for Sudoku. I don't have an algorithm that produces this, but once somebody puts this link over here, it's very easy for me to go and check that this is the right answer. Similarly, if somebody says I have a route which can be done in 5 hours, I can actually look at his route and check, does it take anything less than 5 hours or 3 hours? I can do this one. Factorization, if somebody says I have a large number and says this is what it breaks up into, I can multiply these numbers. Here I'm going to use the fact that multiplication is an easy thing to check that this is in fact. So these 4 problems, even though they are hard, even though I don't know how to solve them, if somebody, some omnipotent being, suppose they are able to solve it and give me the solution, I can verify that their solution is correct. All these 4 problems have this feature, and the reason I'm not able to put chess here is, chess, if somebody says this is a winning strategy, I don't know how to check that it's a winning strategy. These 4 problems have this sort of feature among them. That is, they have this feature that I might not be able to solve them, but given a solution, I can check that you can solve them, that the solution is correct or not. So there's a way to check the solution, and this sort of leads to our next class of problems, which is what we'll call NP, which is those problems which are easily checkable. Unlike P, which was the problems which are easily solvable, these are problems if given a solution to me, I don't know how to produce a solution, but suppose you give me the solution, I will be able to check it. It's all problems which have a solution that can be verified easily. Formally, it's a class of problem for which there exists a deterministic time, polynomial time verifier. And you should contrast this with the definition of P. So P was the class of problems which I know how to solve. NP is the class of problems for which if I don't know how to solve it, but if somebody solves it, they can show me, they can convince me that they have solved it correctly. It's not like somebody says I have solved it and you don't know how to believe. You can actually, they can prove to you that they have solved it correctly. So if you actually see this picture, so this was our old picture. We had P in which this, and NP suddenly, all these 4 problems sort of fit into this class of NP. So among our hard problems, even though we don't know how to solve it, these 4 problems had this particular feature among them. Chess is not a problem. We think it's even harder than this. It's not, I don't know, even if I know how to solve it, even if there's a person who says can solve chess, he can't, I don't know how he can convince me that he or she has the best strategy for chess. Chess is not yet, there's not a problem over here. So I've been talking about, so what's the point of this characterization of hard problems, NP? By the way, you should notice that this characterization, NP includes P. So certainly if for problems in P, if I am able to solve it, I can also check it. So this is an unfortunate terminology. NP does not stand for not polynomial. It's a historical reason. This is non-deterministic polynomial time, and this is how the classes have been defined. So what's the significance of NP? Why do I care for this classification problems? That in suppose I'm asking for hard problems which I don't know how to solve, but yet if somebody gives me a solution, I can solve it easily. What's this one about it? So this is not the perfect analogy. In fact, if you really know, you can poke several holes into my analogy, but it's a good analogy to keep in mind. For instance, I'm a mathematician. I hardly know how to draw. I don't know how to play any music. These are things which for me are extremely hard problems. But on the other hand, when I do see a good painting, when I do listen to a flute recital by Shaurasi or somebody, I can see that there is some brilliance in this one. So these tasks might be hard tasks for me, but when this is rendered by somebody out there, by this one, I sort of am able to appreciate it. So NP sort of trying to capture this notion of things which, even though I'm not able to do it, when there is a solution for it, I can see that the solution is correct. I can appreciate the solution. It's sort of trying to capture these things which are hard, but yet I can understand that it has been solved. So given this, we can ask, so I defined 2 classes, P and P. Do we really know these are different classes? It might be the case actually that everything in NP actually is P. This would spoil all the fun of Sudoku and all of this, but it will be great for the Flipkart delivery guy because he's able to easily come up with the root. This one. So this basically, if P were equal to NP, this would mean every problem whose solution can be checked easily can also be solved easily. Is that the case? That could be the case. If P were not equal to NP, this means there are problems which you can check easily, but yet can never solve easily. And actually, we don't know which of these 2 worlds we live in. We don't know whether we live in the P equals NP world or the P not equal to NP world. In fact, this is one of the central problems in mathematics and computer science today, is asking, is P not equal to NP or P not equal to NP? And this is basically the problem which I talked. We have these few problems which we consider which are easy, a few which we consider hard, but they're not they're hard in the sense when somebody solves it, I can check their solution. Those are problems in NP. And what we want to ask is this sort of, are these 2 classes? It's conjectured that actually these 2 classes are different classes, but we don't know how to prove this. This has been one of the 6 millennium open problems in mathematics for the last 3-4 decades. Yeah. And we don't know how to solve this. So let's go back to our analogy about this one. So why is this problem such a big deal? So you saw this one I told you about this one. NP sort of captures those problems for which I don't know how to do it, but somehow if somebody does it, I can appreciate what's done. So it sort of, NP captures these problems which are done by geniuses. And what we are asking over here, the P not equal to NP question, is sort of a computational or the mathematical analog of this question, can genius be automated? It's the closest you come to this question. This is not, as I mentioned, this analogy is not perfect, but it's the closest. Asking whether P is equal to NP is the question, can genius be automated? Can things which you appreciate, if you can appreciate them, can you actually do them yourself? And that's why it forms one of the central questions in this one. If this is sort of a meta world question, meta question I'm asking over here, but if you frame it in the mathematical language, this is what this question essentially means. It's asking this P is not equal to NP, and this is sort of the understanding of the world we have done. Okay, so we have understood these problems. But I'd like to understand, is there a little more? So notice that these problems are hard. We are trying to understand. We would like to do several things. Firstly, we would like to see if we can actually come up with better algorithms. If we can't come up with better algorithms, we would like to understand why they are hard. This is one, and we are sort of trying to find a structure, sort of a method in this hardness. Is there something I can talk? And this is one sort of understanding of these hard problems we have put here. Another thing we can ask is, are these hard problems, each of them hard of a different nature, or are they somehow related to, comparable to each other? That is Sudoku any harder than the Flipkart delivery problem? Is map coloring any harder? Is factorization? Which of them is the easier problem? This seems like a sort of a weird question to ask. You're trying to compare apples and oranges. You are asking, if Sudoku seems to be a puzzle that you're solving, the Flipkart delivery problem is an optimization problem. This also is another optimization problem. How can these problems even be related? This is a problem from number theory. How does one even expect these problems to be related to each other? Strangely and surprisingly, actually, you can show that these problems are fairly related to each other because of the way we have defined them. And this comes from a basic concept in computing and mathematics called in which we will try to reduce one problem to another. Sometimes for these problems, we'll show that if you have an algorithm for one problem, I don't know how to come up with the algorithm, but if you have an algorithm, you can use that algorithm to compute another algorithm. So somebody gives me as black box. They say, I know how to compute it. So you use that somebody to solve another problem. So some of the problems, if you give me a way to solve problem A, I might be able to solve problem B. What will this tell you? This tells you that problem B is no harder than problem A. If somebody gives me a way to solve A, then, so let's actually look at this carefully. What I'm going to ask is, if somebody tells me how to solve a particular problem A, then I can solve this particular problem B. So if somebody gives me an algorithm for problem A, this means I can solve problem B. This is the notion of reduction. Of course, question we would ask is there a reduction between these two problems? Strangely enough, what we can show that if somebody actually really comes up with an algorithm, a Sudoku solver, we can use that Sudoku solver to solve any problem in NP. I don't know how to come up with this algorithm, but once I come up with the Sudoku solver, I can use it to factorize. This seems bizarre and strange, but this is a true fact. This we know. I don't know how to do this. I don't know how to do this, but what I know is if you do this, I can do this. Huh? No, so we give a reduction. I tell you, you give me this algorithm. I can use this algorithm to convert it. So what we will do is we will build an algorithm that uses this algorithm. It makes calls to this algorithm. So when you write a program, you have subroutines and stuff. So you will write an algorithm for, say, I want to factorize a problem. You will convert the factorization problem. So something like this would happen over here. So I want to factorize a large number. So somebody gives me, say, 1541. So from 1541, so I will give a procedure of the following type. From given 1541, I'll give you a method to construct a Sudoku puzzle. And then I'll run the Sudoku puzzle algorithm on this, get the answer to it. So it gives me the answers to this, the filled answers. And from this, I'll get back this one. So I know how to do this, though I don't know how to do this process. So this is what the Sudoku solver does. These two I will tell you how to do. So I'll give you an algorithm that takes the given input, convert it to a Sudoku input, and then use the Sudoku solver to solve Sudoku, and then the Sudoku solution converted back to this. So you can sort of...
So we are reducing problem A to problem B.
Yes. So I'm reducing now factoring. What I've said over here, I'm reducing factoring to Sudoku. I'm showing that factoring is no harder than Sudoku. So, and what the statement over here says is, if I can solve Sudoku, then in fact I can solve any problem in NP. So Sudoku sort of, it might seem like a puzzle or sort of a useless problem to work with, but in some sense it is a problem which is as hard as any other problem in NP, and this is something which we know how to do. I don't know how to do this, I don't know how to do this, but I know, give me this, you know. So these are sort of statements like if pigs pigs can fly, what's the statement? If horses can fly, pigs can whistle, sort of statement. I neither know either of them are true, but I know how to move from one to the other. Yes.
So you mean to say that this has been proved?
Uh-huh.
Any of the solutions to any of the NP problem can be used to solve any of other NP problems.
So I didn't say that. Right now I just only said about Sudoku. I said if you can solve Sudoku, you can solve any other NP problem.
So I mean, so this statement has been proved in.
This is a statement that's been proved. This is a statement we know to do. So this, in that sense, this is what I want to say. Sudoku is as hard as any other problem, and so in some sense it is the hardest problem in the sense. This we know of. This we know already. We don't know how to solve Sudoku. We don't know how to solve any of them, but we know this reduction. So it's sort of, these two problems are up there, neither of which I know how to solve, but I know how to map these problems one to another. And that's quite a good understanding of these problems. Yes.
How similar is it to transfer learning that is being done right now?
What is transfer learning? Or
The parameters of the algorithms of one problem is transplanted to the other?
Yeah. So we were given, you're talking about how do the sizes of the two in the reduction, how do the sizes relate to each other, or?
No, I'm just saying like you're basically, if you have a problem that is solved, okay,
Yes.
then you'll be using that to train your algorithm, right?
These are not learning type of algorithms. I'm just going to move from one algorithm to another. So give me a factorization problem. I will from it pull out. I'll translate it to a Sudoku problem.
Okay.
You run the Sudoku solver, and from the solution of the Sudoku problem, I'll get back the solution to the factorization problem. So this, on the face of it, doesn't have a learning component, but you can, yeah.
So do you mean all known NP problems today, or do you mean all NP
I mean
problems?
all, so here, it's not just known NP problems. I'm just going to use the definition of this statement. Is a very strong statement. It's not just the problems which we currently know now, the few problems which I put up in NP. So NP is a particular definition. It's those problems which can be checked easily. Just take that definition. If it can be checked easily, then using that definition of the problem, it's sufficient. I can show that, so I can solve it Sudoku. So tomorrow you show me some problem is NP, that problem I can solve it using a Sudoku solver. It's not just problems which we today know to be in NP. It just follows from every problem which falls in NP by definition. Yes.
So why are there only two equalities used, or relation, like not equal to and equal to?
Huh?
Why there are only two relations used? Why can't there could be another relation?
Like what?
Like this P and NP, we are using only two relations,
The-
equal to and
These are two classes of problems, one contained in the other. So either they are equal or one is a superset of it, and that's what I'm asking. So this picture which we had, so actually go back. This picture which we had, we already know this is the picture which we have. These are the class of easy problems. This is one class of, is a subclass of hard problems. And all I want to know is this, does this collapse all the way to this, or actually is this? So that's the only question which you can ask over here, and that's the question which I'm trying to say. So we're sort of saying Sudoku right now, what I said right now, Sudoku is sort of the prototype hard problem over here. It's not, if I can solve this problem, if this problem falls into P, it will not only fall into P, but it will bring with it all the other problems. If somebody wants to show NP equals P, all they need to show is Sudoku is in P. Once that falls, the whole class will collapse to P by what we just said. Yes.
I can rephrase this question.
Mm-hmm.
He's asking why are you asking this question and not some other relationship question? Like you have a relationship of P being a subset of NP. Right?
Yes.
So that relationship, there could be other relationships. Maybe you would be asking what kind of subset. Instead, you're asking specifically equal or not equal, and what is the important class?
You could ask how different are these subsets and this one, but the very least what we would like to know is, are these different subsets? Are these two different classes? Even that we don't yet have an understanding. Later on we can ask, is there a hierarchy, how different, once we know that they are different classes, we can ask how different are they and stuff, but this is the most basic question which we would like to ask, and even that we don't yet have an answer to. If sure. Where did I use it? This is a theorem. This is a theorem. It's a theorem from the 70s. It's yeah.
Yes, that's fine. I mean, you use the fact. I am considering that what you want to say is that we have an intuitive grasp. Not
no. It's not an intuitive graph. This is a
theorem.
I have that procedure which I gave you. I have an algorithm that can take a factorization input, convert it to Sudoku input, and then once it solves Sudoku input, it will convert it. These two, I have two algorithms of this type. For every NP problem, I have these two algorithms. It's not an intuitive grasp. It is a well-known, established theorem. Or it's a fact, as I said over here. Yes.
So according to this fact, like for traveling salesman problem, I am sure there can be multiple solutions, not unique one.
Yes.
Yeah, and for Sudoku, there is going to be always unique solution.
Yes.
So how do, I mean, the algorithm for both of them is can be mapped. I mean, how the both.
So I never say, so notice these problems. All they said is they will give you. They're going to check if they're going to give me a solution. Then I never said they're going to give me all solutions. See, if once you give me this solution, it will tell me, it will give me a solution for the traveling salesman problem. It will give me a route. So no. So that I don't. That. Yes.
That means the optimal solution of traveling salesman.
That we don't have a guarantee. It's not the optimal solution. It will give you a solution which runs in this one. Yes.
Are there any constraints on the coding and decoding parts of the thing? So the method that you use to convert Sudoku to
rather the other way, factoring to.
Are there any constraints on that? Because you could have an exponential.
No. So what we know is those two conversions are actually efficient algorithms. They are polynomial time algorithms. We know that. That's the reason why this fact exists. That is, these things, there are no constraints. That's not the, if you're allowed to do an exponential blow up over here, this fact loses all its importance. The fact that this conversion and these two code, there are these two pieces of code being written here, and both those codes are running in polynomial time. Yes. So this sort of among the problems we would like to understand hard problems, what we have shown is even though there are there's a class of hard problems, Sudoku is sort of a prototype hard problem in this class. And actually what we know is not just Sudoku, actually a whole bunch of problems, Sudoku, map coloring, flip card delivery, several of these problems all happen to have this feature. Each of them have the feature that is, if I can solve that particular problem, then if I can manage to put that problem into P, it brings with it the whole class of NP into this. So sort of these are all what is called the prototype they're candidate hardest problems in NP. They capture the hardness of this one. So we know that these three problems. In fact, today we know several problems out in NP complete. And notice I have not put factorization over there because we don't yet know if factorization has this feature. If map coloring is easy, factorization is easy. But we don't know the other way around. If factorization is easy, I don't know how to prove map coloring, flip card or Sudoku are easy. There are some of these problems in NP for which I understand that they're the hardest problems. There are other problems which are potentially possibly easier than this because given a solution to this, I don't know how to come up with a solution to these problems. So sort of these NP complete problems live or die together. If any one of them becomes easy, then all of them are easy. It just brings with it the whole thing. If any one of them is hard, then all of them are hard because it can't be that one is easy and the other is hard. The moment one becomes easy, it brings with it the whole class. So they sort of live together. So all these problems over here, they are of the same complex. They are either all outside P or they are all inside P. They're all simultaneously hard or they're all simultaneously easy. So even though this is a very surprising fact for us to understand that even though we don't understand how to solve these problems, we know that these problems are all equally hard. So sort of gives us a better understanding of these hard problems. So if somebody tomorrow wants to say, I want to solve NP versus P, they can pick their favorite problem over here and try to map that problem alone over this one. And if you just show that problem is not in P, that will also show that NP not equal to P.
Sorry, just a quick question. So what might be the real world implications if P was equal to NP?
So what was so what would happen? So several we have notice these are all in very interesting problems. We have a whole bunch of optimization problems. In particular, I framed it as a Flipkart delivery problem. That's one optimization problem. There are a bunch of other optimization problems over there. All of them will have extremely fast algorithms. So suddenly you are in a world in which you have fast algorithms for every for most problems we care about. Chess is not in the picture, but several other, these are not the only problems over here. There are zillions of interesting problems which we care about, which are sitting over here. So if any one of them, if P were equal to NP, it means that we have an easy algorithm for all of them. Suddenly it becomes an algorithm's paradise. That is, suddenly you have good, fast algorithms for this. So a lot of these problems, we don't know how to solve them. They are very hard problems. And we do face them regularly in this one. For like airline scheduling, all of these are hard problems. All of these are known to be over here. We don't know. It would be great if we could put them into this one. That's why it would be great if we could collapse them into P. We don't know. And NP equal to P will be this algorithm's paradise. You will have an easy algorithm for all of these problems simultaneously.
And what would happen to things like encryption and security?
To Sameer's question, okay, so we understood some notion of what easy problems are, some notions of what hard problems are. We got some better understanding of what easy, among the hard problems, there are a bunch of hard problems which sort of live or die together. But we can now come and ask, so what if you have some hard problems? Can you actually, what we want to do is, this is not something which we've done in real world, but we want to use, can I use the fact that some problems are hard to my advantage? Can I this seems sort of really weird. I want to ask, my inability to solve the problem, can I use it in a positive sense? This seems a strange thing to ask. Why would one even expect such as this? And for this we had asked, this comes to the definition of what we meant hard. What I meant hard is, it's not just hard to be, it's hard for any polynomial time algorithm. It's hard for me, it's hard for you, it's hard for potentially every other person, this one. So potentially it's hard for even an adversary who's trying to break into my bank. It's hard for that person also over there. So can I use the fact that something is hard to actually into my advantage? And this very idea is what we're going to use, show that if problems are hard, we will be able to use it to our advantage. This is basically what I said. The fact that it is hard means it's hard not just for me, but for everyone. It's not a subjective definition of hard. It's hard for all computationally bounded people, and in potential, it's hard to a potential adversary who wants to break our security. And this sort of forms the reason for such hard problems existing is the basis for modern cryptography, which was what Sameera was alluding to, so encryption and decryption. So let's spend about 5 minutes or so on trying to understand how we are going to use these hardness in a positive sense. So this is something we are very familiar with. We log on to our bank websites. We very frequently, when we buy things on the net or on our phones, we enter our credit card details, and we do this with the guarantee that somehow this data, we're giving out fairly confidential data. We're giving our password, we're giving our credit card details, various of these along these transactions, but hoping that somehow we are not going to get compromised. In most cases, almost surely we are never compromised. Why is that the case? Because we would say, the reason we say is because these details are not going as clear. When we type them, they are not going as clear text over the internet. They are going as somewhat of encrypted data. When we enter our password, when we enter our credit card or some bank details, these things don't go on the internet as raw data. They get garbled and go as encrypted data. But why do we still trust the encryptions and so? Why do we believe that a person who's sort of reading these things on the internet, why can't he decrypt the encrypted data? Why can't he ungarble the garbled data over there? Why can't he pull it out? If he or she were able to reverse this process of encryption, then that compromises all our security over here. So we'd like to understand, why do we trust this? And the reason we're going to trust, so what do we want over here? We want this sort of a process. We want, when I type my password, I want to go to a garbled form of my password. This I should be able to do at my end. When I'm typing it in my browser, I take my password, convert it to an encrypted form. This should be an easy process. But for anyone who sees this, trying to come do this should be a hard or impossible task. Only if the encryption has this feature then it's a safe, secure encryption. So I want a process in which going from my data to the encrypted data is an easy process. From the encrypted data coming back to this one should be a hard process. Actually, we need one more feature, but for the purpose of the talk, all I want is just these two arrows. I want this direction to be an easy direction and this direction to be a hard direction. How do we guarantee such a thing? It's sort of like, of course, in the real world, we do have such thing. When I take an egg, I can make an omelette out of it. That's an easy process. But from the omelette going back to the egg, that's an impossible process. We do have examples of it. Of course, I don't know how to do this. I don't know how to base this one, but we have already seen an example of this. We have multiplication and factorization. There are two such sort of sister processes sitting together. Given two numbers, we know how to come up with this large number. This is an easy process. But this direction is the hard direction. We don't have any algorithm for factorization yet. Factorization, we believe, is a very, very hard problem. So it sort of looks like this, which we want. And in fact, this is the basis for most of modern cryptography. You use the fact that factorization is hard. You use basically these two assumptions. You use one, that factorization is hard, and two, the other person who is also trying to break the security is also a computationally bounded person. He's a fellow human. He's not powerful enough to solve factorization. Once you make these two assumptions, we do have these two assumptions sort of lay the foundation for the modern cryptography. So we have encryption and decryption. So this actually says why we would like problems to be hard. If problems were hard, we have this. If factorization were really hard, then we had this. If factorization were easy, all of modern cryptography will just collapse. So there are advantages for hardness over here. I more or less come to this one. If you notice, among all the things I should mention, one of the problems, checking if, yes.
So yeah, in this slide, there is an intended audience for E of X and there's an unintended audience for E of X, right? So
yes.
The intended audience needs to be able to figure out X from...
So that's what I said. What I want is not just a one-way function. What I want is actually what's called a trapdoor function. So the intended people, so there should be the intended people, that is the person whom I'm sending it to, must be able to break this. So there's a notion, this is why public key cryptography comes. You have an extra key. A person who holds, a person without that extra key should not be able to do this, but once he has that extra key, should be able to do this. So we'll have to see if we can, factorization does not give us one-way functions immediately, but we can see if what we want there, what you're asking there is something called, the next step was called trapdoor permutation. That is, it's hard this direction, but there's sort of a trapdoor which lets the intended audience to open it.
Okay.
And we can do that also from using existing hard problems. So among the various computation problems I talked, one problem which was checking if a prime, which is sort of was easier than factorization. I didn't say where in the complexity classes it fell. And actually, there's a remarkable achievement from 3 researchers from IIT Kanpur about 15 years ago who did show that checking if a number is prime, though factorization is hard, in fact, the checking if a number is prime is actually in P. Previously, we did believe this was an easy problem. Previously, we had randomized algorithms for it, but this was an achievement which happened about 15 years ago. And so sort of among the computational problems we talked in, checking prime actually falls here. Though factorization is over there, primality checking is over here. I think this more or less comes to an end of what I wanted to say. I'll open the questions. Yes.
I had a question related to building of temples and building of pyramids. So it is a severely, I would say, NP problem. I mean, we can check if it's correct. The dimensions and everything do come correct. But how was such a problem achieved? Was there an algorithm to build that entire series of stones or steps, or the entire thought process?
No,
or were there any algorithms, were they lost in between? Or
no, certainly there was huge losses, but these are sort of something which I fudged along. When I mean an algorithm, so they're always, when I mean an algorithm, I want an algorithm which solves it for every input instance. These are what we see are the temples, the pyramids which were constructed can always have, they can be a hard problem in which there might be one factorization instance which I'm able to, one large number which I'm able to break down into its components. That's not what I mean by an algorithm. An algorithm is something which solves every instance of the problem. So specific instances can be solved, but also these problems, pyramids in this one, there was huge amount of mathematics that went into this one. People did, the Greeks, the Indians, everybody out there, the people who solved them, knew geometry very well when doing it. It is an extremely algorithmic process over there, what they did. This is not a magical process. There were architects there who were following the principles of science and engineering to construct this. This is not something came out of the blue. There were scientists in every sense of the word who constructed these temples and these marvels. You should appreciate the engineering and science that go there. These are not hard problems. They put in a lot of effort, but they knew that there were architects who did this.
So factorization, what about that? Like, is it harder than NP complete, or is it
No.
easier?
So factorization, it's a problem in NP, so it's not harder than NP complete. Certainly, it is a problem in NP. So factorization is a problem in NP, so it's no harder than any NP complete problem. We would like to show it's as hard as any NP complete problem. We don't know how to show this. It's a sort of problem which is sitting in this interim between P and, it's a problem in NP which is sitting in between NP complete and P currently, but the guess is it's actually a very hard problem. I must here mention, given that you asked this question, so it's very hard in what's called the classical world, where in our set of computers, there is this other world which is being explored, in which if you have quantum computers and stuff, factorization, strangely enough, becomes an easy problem over there. If quantum computers become the feasibility, sometime tomorrow, actually factorization will become easy. And in fact, it will bring down with it all of modern network security will collapse if quantum computers become feasible tomorrow.
So giving a P solution for Sudoku doesn't prove P equal to NP?
Yeah, no. Giving a P solution for any NP complete problem will collapse all of, so if you give me a Sudoku solver, that scales well with size, that will collapse all of NP.
But factorization was outside that, right?
No, factorization is in NP. It not only collapses. If I collapse Sudoku to here, it will bring all of NP, if I bring any of these problems into P, it will bring all of NP into P, which includes factorization over here.
Okay. It was in the beginning checking if prime was a hard problem, NP problem. Then after finding an algorithm, it came into P. So like this, we do not have a guarantee if a Sudoku is solved, it also can fall into P.
Yeah, certainly. So no. So that we have a guarantee. So primes was not, so there's a difference between that. So primes was not a problem which was sitting in NP. Primes was a problem sitting somewhere over here. From here, it can fall into this without doing it. But if any of these problems fall over here, it will bring with it the whole. If you give me an algorithm for an NP complete problem, yes, it will bring down. If you give me an algorithm for any of these problems which are outside P but not in NP complete, that doesn't say that the other problem all of NP. So primes was somewhere sitting over here, prior to this. So primes was not completely outside, as I said. So this animation, it's supposed to come from there. It's supposed to come from here and drop in. Yes. So chess is, so you have to define, so all of these you have to define, so a version of the problem which scales with input. So you can ask, chess is the usual, take the usual chessboard, generalize it. So usually 8 by 8 thing. So generalize the thing to 8 by 8, 10 by 10, and so on. And there's a particular generalization of chess which makes chess into, so even before that I said chess comes in the, unlike, so chess and Sudoku are two, they are both puzzles, but they are slightly different. Sudoku is a single player game. Chess is a two-player game. Chess, Go, and these are sort of two-player games. Typically, most two-player games fall into another class. There's another class beyond this called P-space, and they happen to be complete problems for that class. Chess, actually, there's a particular generalizations of chess which is even out, which is actually exponential time. It shows that chess is exponential time complete, but this depends on how we are going to scale, how we are going to talk about generalizations of chess.
I'm asking that question because we've had.
Let's just get, let's use the mic so that everybody can hear and there's,
We have this deep blue which, war against Kasparov.
Yes, so deep.
So and then that means there exists some kind of algorithm there.
Yeah, so it's unclear. So what Deep Blue, so yeah, so there's been Deep Blue, there's even more recently there's been AlphaGo which works just remarkably well for Go. But these are not algorithms which necessarily work well for chess in the scaled version. They work well for the current chessboard problem. It's unclear how they perform this one. And they're able to beat other chess players. It's unclear whether they beat every single. So when I want an algorithm, I want something which works for every single this one. They're able to beat fellow chess players. They're able to beat another this one. It's unclear whether that means that they can actually beat every single strategy out there.
Just take it as like there are programs available now to run on a phone and be deep.
No, I'm interested in that only in the sense that they do fall among solvable problems.
No. So for example, the Flipkart delivery problem, which I said over here, each of these problems, what we do know is there are several instances of these problems for which we do know how to solve them in practice. That might be the case, but still these problems we do believe that we believe firmly that we don't have algorithms which solve them on all cases. They have instances when they've solved with other people, all the natural instances they are solvable. It's possible that way. Yes.
Sorry. To go on a tangent, Prahladh, where would you say aesthetic issues fall within this range? Aesthetic. Talking about aesthetics, how would you kind of deal with it? And is it possible for an algorithm to decide aesthetic issues given that it's not easily checkable and there is no one answer?
Yeah, so this, I don't know how to do it. It depends on this one. People have tried to do these things, but I don't know. It depends how you're going to frame. This is going to be more a matter of definition. What does it mean? The aesthetics, I'm bringing in subjectiveness into the problem.
Can you say that how is it reference to time? If is it because that it does take too long? Is that step 1, step 2, step 3?
Yeah.
If I have an algorithm which time is no longer a restriction, then do all problems therefore fall into P?
No. So time is always so this is an assumption, hypothesis which we are making, that there is only at each step we can only do some local operation. That is,
yes.
We can locally, so we have the data with us, like we had addition over there. At each step, we can do a very local operation. We can just handle 2 digits at a time over here. So that's our limitation. Any algorithm has to, at each single step, it does only a very local operation. So an algorithm is a sort of a concatenation of several local operations. This is, and once you have this, you will ask how many such local operations you need to do in order to achieve the final this one. And if you're going to charge for each local operations, which you will, any algorithm has to have a local. You can't say it just takes an input, just magically produces an output. When you mean an algorithm, you only look at the data locally at each place. You do local manipulations. Once this is the notion, so this is a sort of abstraction of a computer I'm going to take. That is, each single step is only a local manipulation. That's the sort of, actually, that was Turing's abstraction out there. And all computers, this is a hypothesis, this is an assumption we are making, that computers can only handle data this way. Each time they do a change, it's a local change. Once you make this assumption, all of this falls into place. And every single computational device that we have built till date satisfies this feature. Of course, you can come and tell me there is another computational device which has a different one. We haven't seen this. This is in fact called the Church-Turing hypothesis, that all computers have this feature.
Thank you.
So why is the difference between easiness and hardness dependent on polynomial and non-polynomial? Because something that's n to the power of 5 is still really hard.
Yeah. So this is right. This is a very fair question to ask. So the problems I talked about here were like n squared. These are very nice problems. Why did I put in n to the 5, n to the 6 also over here? Right now, this seems to be a nice distinction between these two, given that we don't understand this one. Once we begin having a better understanding, there's already been a whole class of work which goes trying to understand, differentiate problems which are n squared from problems which are n cubed, n power 4. This is the first understanding which I need to get, polynomial versus non-polynomial. And once we have such an understanding, we'll go for a more, this is what, it's a very active area of research called fine-grained complexity, which is active, in which you ask about, you differentiate problems from n square versus n cube versus n power 4. This, yes.
In the second last slides,
yes,
you know, the encryption where you showed that x is equal to e, you can I mean, you can pass that to e into x, but is it, you know, the hackers, they use permutation and combination, so that way it is, some way it is possible to come to that x solution, I mean, the number.
No, certainly what one could do.
I mean, there are ways where the people, you know, they can encrypt, de-encrypt that.
You're asking is, that is, you can,
yes.
Of course you can sort of, the one way to do decryption is just do a brute force, run over all possible x's, find out which x give you this e of x. If you're going to run over that, that's certainly, that's an algorithm.
But it's a time process.
Huh?
It takes
too much time.
Too much time.
I believe the adversary who's trying to break it is also bounded. If he's going to be unbounded, I'm not going to be fight against the adversary who is extremely powerful. I'm making the assumption over here that the person whom I'm going to fight against is a bound. So he cannot do this task over here.
Yeah, because you have written hard and impossible.
Yeah.
So it can
no,
be
when
hard.
I mean impossible for computationally fellow humans.
Of course, for a layman it is.
Yes.
Thank you very much.
So back to the classification of problems slide. You'd mentioned that, so I think there's a couple of things you mentioned. One was every problem has sort of a dual problem, which is the verification, right? So there's a problem and there is a verification, which itself is a problem.
There's a search, some problems have the search problems have a verification aspect to it, yes.
So checking prime used to be a NP problem, but you know, when we, at some point, someone found an algorithm to, what is the verification problem for a checking prime?
So so this is checking prime. The other, checking if it's not prime, there's an easy way to do it. Checking if it's a prime, there seems to be no easy way of it. You can use number theory actually to show, it'll take me a while, but you can actually give me a proof that a number is prime without actually, it was known that primes are in NP even before primes were shown to be P. It was actually quite an achievement from the late 80s or early 90s. There's a result of Pratt who showed that prime is in NP. It requires a bit of number theory to do this.
Okay, no, the framing of the problem is what I'm unclear of. So for example, the problem statement here is, given a number P, is this a prime? Yeah, so that is the problem statement. What is the verification of this?
So so I can give you a proof. So I was quite sloppy about the definition of NP over here. So what does it mean if a problem is NP? Problem is somebody who can solve this problem can also provide to me a proof that the thing is solved. So they can so primes you can provide to me even before, right now of course primes has gotten into P, but even prior to this I could provide to you a proof and show that I don't know how to come up with the proof, but you could give me a proof that this number is prime. Doesn't seem obvious, but we did know this.
Okay.
Sir, can we analyze all the results and arrange in a logical order and find the optimal solution for a particular problem? So NP problems can be solved to P, I think so.
So we don't.
Are we able to analyze the data set of the solutions?
No.
Or we can consider a part of the data solution.
No, but what?
And arranging in logical order.
Yes.
And then by using search methods or something, binary search method, we can drop down to an optimal solution and find the answer.
We don't know how to do this. If we knew how to do this sort of search, these are basically search problems. We are trying to search for a good coloring here.
I'm trying to take it the back way, not going from NP to P. Means I'm trying to analyze the solutions and arrange in logical order. We don't have the solutions, all the solutions possible. Okay.
Yeah, we don't have.
That is the main problem.
So there are exponentially many solutions. We need to search among these solutions, and we don't have, the only way we know how to search is just a brute force search among the solutions.
Yeah, so I think all the questions are technical. I want to ask you a very different question.
Okay.
For a researcher in this field, right? What do you find most exciting to be working in this field? What really gives you the kick that, yes, this is why I want to work in this? You know, what makes you feel that this is really what? That's a hard question.
And it's non-verifiable. It's non-verifiable.
Yeah.
No, this.
What do you like? I mean, what do you think about,
This has been a very high-level talk, but there's a method. These problems are hard. There's a method to the madness. There's a you might think of these problems as very disparate problems. But there's an underlying structure to them, and seeing these structures between them is enjoyable. It sort of satisfies your curiosity, and yeah, I don't know how to else to.
So I'm going to close this talk over here, and he is available. And Prahladh, thank you. You've taken us through quite a journey with P and NP and easy and hard. Thank you so very much for this session. Just a quick